Hi, welcome to this lesson about goroutines, which are Go's take on threading. Here I have a very simple program. It prints hello, and we're going to make it print hello world now by calling the world function. Okay, and let's just run that, and you should see the answer. The output is pretty simple. We should get hello and then world on the next line. So how do you add a thread? Well, there we are. We just stick go in front of any function call, and that function gets executed in a goroutine, which is Go's version of the thread. So what would happen if I just ran that? Will it print hello world? No, because now that this is a thread, it needs to get scheduled, and the program ends right here just after we've created the thread, and the thread has no time to run. So we could just do something pretty obvious. We could put in some time. Just put in a single second sleep time, but of course we have to import the time package. Okay, now what happens if we run it? Great, we get hello and world. This is not unbelievably useful, I would say, obviously. We could make the function more complicated and do a bit more processing and so on, but here are the basics anyway. It would be nice to get rid of this sleep though. So how could we synchronize, how could we wait for this thread to end? Well, there are quite a lot of different mechanisms for doing this, and you have wait groups and mutexes and so on, but my favorite mechanism in Go is called a channel, and this is what I want to use. So a channel is a communications mechanism between two threads. It can be bidirectional, which means one thread can put something into a channel and another thread can read, and then vice versa. Goroutine A here puts something into this particular channel. It can be any type that you like. Channels are typed, so you can have a channel of type int or a channel of type string, and then you can put strings or integers into them, or more complicated types. So goroutine A puts something into the channel, and then goroutine A is blocked until B has time or decides to read from the channel. And so that forms a kind of synchronization point. And channels can be bidirectional. That just means that B can put something into the channel and A can read it. And it will be blocked until A reads it. So what is the point of the channel here? Well, I'm going to use a channel to indicate that this function has had a chance to complete, and I want to wait for that a message to come out of that channel so that I know that it's finished. So here I'm going to say that first I've got to make a channel. So we'll call it done. Chan, and the type of message that's going to go into the channel, for the moment we're just going to choose int. It doesn't really matter. There we go, int. Okay, and we should pass it in here, function, and before we exit the program, we should get rid of this sleep stuff, and before we exit the program we should read from the channel. Oh, that's the wrong way around. Here we are. The arrow is going to take something out of the channel, so it's pointing away from the channel. And we're just going to ignore what that is. It's going to, whatever the message is, we're just going to throw it away here, because we're just concerned really about getting a message. And up here we're going to say this function takes the parameter done, which is a channel of type int. So chan type int. And when this function is done, we're going to stick a 1 into it. So now what's going to happen is we're going to print hello, we're going to make our channel, we're going to start up our little goroutine, and here we're going to wait until we get a done message from that goroutine, and then we can exit. Here in the goroutine function we're going to print world, and then we're going to put a message into the channel that we were given as a parameter to say that we finished. And if you notice up here, we don't need the time package anymore for this. So let's run that. Okay, we get hello world, which is what we expected. So, what would be a more useful goroutine? Well, there's a very easy example to use, which is quite simple and quite useful at the same time, which is called a ticker, which generates an event on a channel every so many seconds. So we're going to call this one, in fact let's just let's leave that one there and start a new function. Let's call our function ticker, and we're going to have a channel called and what we're going to do is forever we're just going to no, we're going to sleep. How many seconds do we want to sleep for? Well, the ticker should be for some number of seconds, so it should tick every so many seconds. So we should pass a parameter in, and that should be seconds. Okay, and then we should be able to say that we want to say time dot duration. We convert that seconds value into a duration, and we multiply it by the number of milliseconds in time.second. Okay, and to get this to stop being read, we have to import the time package. Okay, and that's not much good because that just sleeps. What we want to do is every time we've slept for that particular number of seconds, we want to issue an event or issue a message, and we're going to do we're going to send a number 1 into that channel. So how might you use this? Well, let's change our names here. Tick channel. Let's type int, and what we're going to do is we're going to create a goroutine, which is the ticker, and we're going to say please tick every second, and send us the tick events on this tick channel, and then we're going to wait for all the events on the tick channel, and we're just going to wait for one event and then another and another, and we're going to do something every time the ticker ticks for us. So we're going to have another we're going to have a for I equals range tick. This is a special use of the range function, which seems to do all sorts of useful things, and it basically looks at it goes through all the ticks that we get. So let's forget about the I, we don't need it. For range tick, we're going to fnt dot I'm just going to print tick every time we get a message. Okay, I think that's it. So this means we're going to just loop, and of course these loops are never going to stop. We're going to have to break the program to make it work. Let's run without debugging. I don't like this output. It's very annoying. Let's just stop the program. Let's go to the terminal and say go run, and then you'll see it better. Okay, so here you can see that our little ticker is generating messages every second on the channel, and here we're reading all of those messages and printing tick every time we get one. That's not terribly satisfying. I prefer to have a clock that does tick-tock. So let us stop this. Control C. Okay. How do we make it do a tock? Well, we can use the same function again, but we need another go routine. Okay, and probably another channel. So let's make another channel and we can call it tock. Okay, and we can make another go routine and make it use the tock channel. And I want them to be offset. I don't want them to happen at the same time like that. That would make them happen roughly at the same time. So what I'm going to do is I'm going to make them last for 2 seconds at each, and I'm going to offset them. Okay, and then I've got another problem, because how do I wait for a message on one channel or another channel? I mean, there are 2 channels now, and how do I get the messages from both of them? Well, I can't use range like this anymore, but I can use the for loop, and then I can use this fantastic thing called select. It's a little bit like a switch statement, but not. It allows you to wait on different channels at the same time. So I can have a case statement here which reads from tick. Oops, sorry. And if something comes in from tick, we print tick. And we can have another one which says case tock. Oops, sorry. You don't have to. You can see we're waiting on different channels, and it is possible with this select mechanism to. Let's just firstly we've got rid of a quote there. It's possible with the select mechanism to add in timeouts as one of the cases. I won't show you how to do that, but it's rather useful. So you can wait on all sorts of different communications channels, and if you don't get a message in soon enough, then you can time out. Okay, so here we are. We've got tick-tock. I would like tock to be louder, so I'm just going to do like that. So we've created our 2 go routines. Each one is going to tick every 2 seconds, but one of them is offset by about a second from the other. So let's go down here and see what happens when we run it. Tick tock, tick tock, tick tock, tick tock. Ah, there we are. Now, actually, in practice, tickers are already supplied. You don't have to write your own in the time library, and they're frequently used for things like, for example, heartbeats, to check that a remote service is still available, and so that you can have a warning if it suddenly becomes unavailable. Okay, so let's look at a bit of information about how threads are scheduled. Here we are. Go has pretty light threads. they have pretty small stack sizes for each goroutine, and they tend to be faster to create, and you can create more of them in general than you would create of operating system threads. So the way Go works for them is it has one operating system thread for each CPU core, and it tries to keep the a certain set of Go routines running on the same OS thread which is attached to the same CPU core, to minimize problems that happen with caches when threads move from one CPU core to another. So this is called the local run queue. There's a global run queue. I'm not going to try and explain any of that, but these Go routines can get their turn to run inside the OS operating system thread, every so often, and they can be. In the old days, they cooperatively multitask. So, a Go routine would get a chance to run, and it would have to give up its chance. That was all done, by the compiler. It would insert these yield points, and it would have to, purposefully give up its chance of running to let another Go routine, for example, have a chance to run inside this OS thread. But nowadays, those are preemptively scheduled too. So here you are, you've got these run queues, local run queues, one for each CPU core. And if you have a particular CPU core which is beginning to run out of things to do, it uses thread stealing, which means it goes and finds something to put into its queue from one of the other queues, and that is an efficient way to distribute load without spending lots of time continually trying to even out queues. A Go routine can get blocked on I/O, in which case the thread that it belongs to is put to one side. All of the non-running Go routines are attached to a new thread, and it starts executing on the core so that they can get going while this one is waiting for its I/O to complete. So, is this better than C, I wonder? Well, it's kind of complicated, but it is possible to show you that Go routines are quite efficient, and you can use them in ways that you might not originally, you might not have thought of. So let's just go and get our... Okay, so where's that window? Okay, anyway, so let's have a look at this example. Okay, here I've got, bring it up here, sorry. Here I've got a directory with a little C program that creates threads, certain number of threads, and a Go program that creates a certain number of threads. And I have to run some setup on this Linux machine to tell C to use small stacks for the threads, otherwise the C code here doesn't even produce any, isn't actually able to complete. But I'm going to run the comparison now. What it shows you is that starting up and creating 10 threads in Go takes a certain amount of memory, a little bit more than C did, and the time is so small it's almost negligible. But by the time you get down to creating 100,000 threads, Go uses about 4 megabytes of memory, and let's see, C has used about 270 megabytes of memory, and it wasn't able to create all 100,000 threads anyway, because it reached a limit, and at which it was told that it wasn't allowed to create any more. And that in any case, even doing the threads that it did took C half a second, whereas Go was able to allocate the full 100,000 in 0.02 of a second, 2/100ths of a second, and it only used, as I say, about 5 megabytes to do it. So you can see there's quite a difference in the philosophy between these two, between how you might think of using threads in these two languages. You can afford to create a lot of threads in Go. That doesn't mean that all of those threads can be active all at the same time and doing work. That's not true. But if the structure of your program suited having large numbers of threads and they weren't expected to all be active at the same time, then you could do that happily, and it would be a lot faster than you might expect. So for example, I thought of having a build system in which every build task was a Go routine, and I've trialed that in various cases. It nearly makes sense. Right, what about an example of something that is more complicated than this? So I do have another project that I was working on fairly recently called chfind. What this is a program to look for, to do hash sums, to compute hash checksums of files that can be quite big, and it relies on a function here called hash. A couple of functions actually. One of them is called hash file, and this uses a rather snazzy hash library that's very fast called xxhash. And we open a file, copy the file through the hasher, and then compute the final, return the final checksum. And I've used this my plan is to, be able to find the checksum of a large number of files, and eventually I want this program to tell me if anything has changed since the last time I ran it. So it's a bit like a part of Git, sorry, or you could say that it's also like a little bit like one of the make build tools, but it's using hashes rather than file date and time to see if something has changed. And what I found running it on my machine is that it can be quite slow, especially when you try to hash a big file. And so I thought this might give me an opportunity for some parallelism. And so, but even when you're trying to do something in parallel, I/O bound tasks can sort of kill that parallelism, because your disk drive can only produce so much output at a time anyway. So here I have a function for hashing big files, which cheats because it reads the front of the file and the end of the file, and it only reads a certain number of bytes from the front and the end. So in certain cases, if you're talking about video files or things like that, that is probably good enough to ensure that you've got, that the header hasn't changed and the nothing has been added to the file since you last used it, and this does make the whole process a hell of a lot faster as long as you choose a small enough percentage of the file to read, like perhaps about 1%, and then you can deal with quite multiple gigabyte files quite easily. So that is all in the sort of hasher part of this program. But where do Go routines come in? So I drew a little diagram. The plan was to have this one routine which is walking the directory structure, and it's putting files into a channel. And the thing is, I've shown you channels that are unbuffered, that have basically one slot inside them. And if you try, once you put something into the slot, you have to wait until somebody takes it out. The buffered channel has a sort of an array inside, and you can put things in and immediately go on and do something else, and then come back and put another one in, and until the channel is full. And then when the channel is full, then you block and you can't generate any more items. And then a reader can read things off the channel at a different speed than you are putting them in, if you like. So here we've got this we're going to have this directory walker which walks around the file system looking for things to compute hashes of, and when it finds something it's going to compute the hash of, it's going to put it into this new files channel. And then we're going to have created a whole lot of little workers which read from the channel whenever they start up, and the first thing they do is try to get something out of the channel, and then they go and compute the hash of it and put it into the hashed files channel, right? And then another little goroutine called the printer reads continually from the hashed files channel and does something with that, like printing it on the screen, or maybe saving it to a file somewhere, to a checksum log somewhere. And that's the basic plan, and it looks pretty simple. And here we have some of the code. Here's a worker, and firstly we've got a structure containing information about the file. When we eventually calculate the hash, what is it? What's the path to the file? What's the other, file attributes? What are the other file attributes? A little variable called confidence, which says how confident are we that in the value that we've calculated. And I just put that in for a bit of fun, because when I explained my earlier trick, with not reading all of a big file, well, that means that we have lower confidence that we that we've computed the hash, that we have lower confidence that we can detect change in that file, basically. And this is how we decide whether a file is big. It's just a constant that we've embedded in our program. I don't think I've shown you constants before, maybe. This is what percentage of big files we're going to read from the beginning and the end. And this is how many of these hash workers we're going to create to do work. And there's not much point in creating too many, because otherwise you'll saturate the disk I/O that's available. Okay, so the hash worker itself needs to have the new files channel that I put in here, and it also has to know where to put its output. So it needs to know about the hashed files channel, where it's going to put the file structure after it's computed the hash. Oops, sorry. To go all the way back up here. And like I've shown you before, there's a little done channel to say when this worker has finished, and essentially it's going to finish when it this is the inverse way around. That's the funny thing about it, because actually no, sorry, it's going to say done when it has not got any more new files to read. So that means the new files channel is absolutely empty. So it's going on the range of the new files channel. It's just going to read all the values it can out of the new files channel, and for each file it's going to decide whether the file is big or small, and it's going to choose which hasher function to use, either the big hasher or the little hasher. And for errors we're just going to insert we're going to have an empty record, and after we've hashed the file we stick it into the hashed file channel, and so on. Here's the printer. This is happening at the end of the code. This is just reading from the incoming, from what it sees as its incoming hashes channel, which is the hashed files channel. And when it's done that, when it's read them all in, it's sticking them all into a map in this case. That's not really, could be printing them out as it got them. Then it just prints out the map at the end, and it sends a done message on its own done channel to say it's finished. And here we have the file walking function. And this uses some utility functions in the file path module to walk a tree, and there's a visitor pattern here. Here's the visitor function that gets called every time the walker sees a file, and it's going to, as long as it's not a directory, it's going to stick that file it's going to create a manage files sort of structure and shove that into the new files channel, and then add 1 to the file count, and that means that the new files channel will have something in it for a worker to work on. And here we are. We've walked the whole tree, and we are going to try and close everything down. So firstly, sorry, I forgot to say at the beginning, here's where we create all the workers, and we create the printer. So we're just creating one worker for, we're getting max workers, and here we are creating the printer, and here we are waiting for all the, we're sending we're reading from the done channel for the worker just to see, has the worker finished, and here we are, we're closing that channel, then we are reading from the printer's done channel to see if the printer has managed to finish printing out all the all the files that were generated. So of course, we can shut down all the workers, but that doesn't mean that the printer is finished yet, so we have to wait for it to finish, and then we can return, and that's all that done. And this program cost me a lot of effort to try and write, and now that I've come to do this video, I can see instantaneously that I've got a race condition, which is that these workers, which are reading from the new file channel, are going to just decide that they've finished if there's nothing in the channel. And so if you don't manage to get anything into this new files channel quickly enough, then all your workers are going to exit. So that is the complexity of the game. I thought I had this all sorted out, and now immediately I've seen that I haven't. Go will do some amazing things. It will tell you if you're deadlocked, and it can also be put into a mode where it will try and detect race conditions. So it's well worth learning a bit about that. But I think that I've sort of overdone it. This is one of the longer lessons, and we could perhaps benefit from doing a little bit more on it later, after you've had a chance to absorb all of that. Okay, cheers.